All right, so people still arrive. Okay. Yeah, so hello everyone, good afternoon. Welcome to the lecture number 4 of our course on quantum computing. And so today we're gonna start the actual like quantum part of our course, right? Today's pretty important lecture. Today we're gonna introduce this concept of Hilbert space, right? So this is a mathematical concept, but it's like very important for quantum computing. And in order to be on the same page, we need to introduce this concept first. And then we will proceed to basics of quantum mechanics. I put 1 because we will discuss the first part of quantum mechanics, of quantum in general today, and the next week we will continue. All right, so let me import the libraries we're gonna use, right? And also, as usual, we enable this multiple output. All right, so Hilbert space, what it is and why we need Hilbert space. So the Hilbert space is a vector space equipped with inner product of vectors and functions, let's say broadly. And the vectors and functions can be complex valued, okay? So it's not just a like Euclidean space or our three-dimensional space where all vectors are real values. So a Hilbert space is a generalization of Euclidean space in terms that it also considers complex valued vectors, right? And we already mentioned that quantum mechanics is based on complex things, so we need complex vectors in the analysis. And this space can be infinite dimensional, okay? So we're not restricted to the dimension of 3, 2, or 10. We consider broadly, we take into account that our space can be infinite dimensional, okay? And yeah, we also imply some properties on this space, like this square integrability. The functions must be square integrable. But let me tell you what I mean by all this, right? So here I summarized what we need to discuss. So we need to discuss how to operate with complex functions as vectors. Okay, so if you never heard about function space, this is the lecture for you, right? So a very important concept in math, that we can work with functions the way we work with vectors. Okay, for example, we can we'll discuss that in what follows today. We need to introduce the inner product of two complex functions. We need to discuss how to introduce a basis in this space to describe basically any function in the space. Okay. And finally, we need to discuss a way how to represent any function in this function space. Okay. So once again, Hilbert space can be, or it is a complex valued space, right? So we're not restricted to real functions, real numbers anymore. We work in the complex space. Second, the space can be infinite dimensional, or in general, it can be of any dimension space. This is second. And third, this space can be vector and function space. So we take into account the both concepts here. Okay. So first, how we calculate or how we introduce the inner product between two functions. Okay, so this is the key point to understand here. So I can describe, I can introduce the inner product, which is scalar product or dot product of two functions, like let's say f of x and g of x, and can also write them using this Ket-Bra-Dirac notation, like this, using this definition. So basically, we write the integral, right, of the product of two functions, f of x times complex conjugate g of x. Okay, so the inner product of two functions is the integral of the functions, and if the functions are complex valued, we have to complex conjugate the second one or one of them. So the result will be the same regardless of which function you can complex conjugate. Okay, and we also imply that the functions can be squared integral, right? So that means that this integral of the absolute value function squared exists. Okay, exist means it doesn't diverge. It can be any number, any value here, right? So if this inner product of two functions is equal to 0, the functions f and g say to be orthogonal. The functions are orthogonal. So if the integral of their product is 0, the functions are orthogonal. Okay. We of course can figure out many examples of such functions, and here I present arguably the most important one. Okay, so if I take function f of x to be equal to 1 over square root of pi cosine nx, where x is just real valued argument and n is integer number, 0, 1, 2, etc. So in fact, this is not just one function, right? This is like infinite number of different functions: cosine x, cosine 2x, cosine 3x, and so on. And of course, I can introduce another function or set of functions, g, n of x, which is the same but sine instead of cosine over here. So it is again a infinite set of functions, sine x, sine 2x, sine 3x, and so on. And we will check, but these functions are orthogonal at the period of these functions. Okay, so the period of cosine and sine is 2 pi, right? So if I integrate the product of these two functions over, from 0 to 2 pi or from minus pi to pi, the result is 0. Okay, so let us check that, and let's check why so. Right, so I want to plot the figures using the SymPy plotting function, right? Because it's just one line of code, so it makes a little bit tidy the things. So I import this plot from SymPy plotting. Okay, and also I need x for these formulas. I need x to use it as a parameter, as a variable. All right, so I plot here the function cosine 3x and the function sine 1x in order to see what's the how these functions look like. Okay, so here's the plot. The blue one is cosine 3x. This even function, right? And this origin one is a sine function, sine x. Okay. So now I take a product of the two, cosine 3x and sine x, cosine 3x and sine x, product of the two functions, and plot the result, right? And I get something like this. So now I say that if I integrate this function from minus pi to pi, I will get 0. And why so? Well, we know that the integral, right, is the area under the function, under this plot. And if this area is above the axis x, it comes with plus sign, right? It's positive contribution to the total area. This area over here in the lower part of this graph contributes negatively, right? So it's negative contribution. And we can find this positive part, negative part here, positive here, negative here, which completely the same, or at least look the same. But anyway, let us introduce this function fn cosine 3x with this normalization factor here, right? And gn, which is sine 1x, and integrate the product of the two functions. So the way we integrate the functions, I use SymPy method. So I write SymPy that integrate then the product of two functions and then the argument, right? So integration runs over argument x and starts from minus pi and goes up to pi. So we integrate the product of two functions and we get 0 as we expected. So again, the product or the scalar, the inner product of cosine 3x and sine 1x is equal to 0. So these two functions are orthogonal. The same way I can change this parameter here, for example, put 11 and here maybe 23. So cosine 23x and times sine 11x, it's also, the integration is also 0. So, and one can check that for any period, right? Any number here, the result is always 0. So these cosine and sine functions are orthogonal. Okay. So next, what I'm doing here, here I plot the result of the product of cosine 3x times cosine 3x. Okay, so now I consider not sine and cosine of different argument, but cosine of the same argument, cosine 3x times cosine 3x. And this function, this total function, gives me a function like this, right? So now this graph is totally in the upper half plane, and obviously the integration of this function cannot give us 0, right? It must be something else. And the way we introduce this normalization factor, this 1 over square root of pi here, leads us to the result of 1. So the integration of this product, cosine 3x times cosine 3x, gives us 1. Okay. In other words, it means that this function, cosine 3x, or cosine any other, cosine 12x, it will be also equal to 1. So, but at the same time, if I change this number, for example, cosine 10x times cosine 12x, 10x, 12x, what I get very sophisticated function, which looks like this. You see this. So sophisticated function, and one cannot say, like, if I integrate this function over the period, would I get 0 or not? But the result is yes, the integration is 0. So the product of any sine and cosine functions gives us always 0, except for one case when the function is the same. For example, cosine 12x gives us, of course, 1. Okay. Which means that these two sets of functions are orthonormal. Okay, so they are orthogonal because all inner products give us 0, except for the case when n is the same, right? Cosine nx times cosine nx gives us 1. So these functions are orthonormal. Yeah. And this is what, and this is this is yet another example of cosine 2x times cosine 3x. Again, function is very sophisticated, and I cannot say in advance if I would get 0 or not after integration of this function, but the result is this, is 0. All right, so why we need this? Why we need the concept of inner product of the functions? Right, so we need this concept in order to be able to work with functions as with vectors. So we can treat functions as vectors. So for example, let us look at this figure on the left with 3 coordinate axes, x, y, and z, the basis vectors e1, e2, e3, right? And when I introduce this basis, this axis, I can describe any vector, like vector A in this space, as a combination like this. So this is just the sum of the products of the vector projections AI times the basis vector EI. Okay, so I can represent any vector in this space in this form. So now, if I introduce the functions that we just discussed over here, this f and x and g and x, okay, and I say that now I use these functions as the basis in my vector function space, I can represent any function in this space using these fnx and gnx functions. So you, of course, recognize what is this. This is the Fourier transformation, right? This is Fourier transform. This is Fourier transform, one of the most important concepts in science, in engineering, and electrical engineering for sure. So we use Fourier transform anytime we work with signals, audio, video, radio. Very important. So every time, so basically we use Fourier transform every day. Even right now, right? I'm talking through this Zoom, and Zoom records my audio and converts to the spectrum, and for some, I mean, it makes the sound more like compact, right? So all these methods use Fourier transform. That's why it's so important. So we say that we can represent any function using this approach of vector function basis. But how I find these an and bn coefficients, right? So these an and bn coefficients are the projections, and I quote this word projections, right? The projections of this function a on each of these basis vector functions. Why? Indeed, if we consider this expression here, we can multiply from the left by this bra vector of one of the basis vectors. I choose fm, vector fm. Right, so multiply this vector on this expression here from the left. So I write it here. And here is the result, right? So next, this an and bn are constants, so I can take them out from the inner product here and here. And here is the result, right? So I have this first term, the product of fmx times fnx, and here fmx times gnx. So this guy is always zero, because the product of any cosine by any sine function is equal to zero. But this one is equal to zero for every m except for the case when m is equal to n, right? So we describe this product, this combination, as a Kronecker delta, delta symbol with two coefficients n and m. And this Kronecker matrix is equal to 0 when n not equal to m, and equal to 1, these elements equal to 1 when n is equal to m, right? So basically this is the identity matrix. Another way to write an identity matrix. So the sum of these elements, an times delta Kronecker over n, right, results in only one non-zero term, am. Okay, so we conclude that any coefficient in this representation, in this series, an, is equal to, indeed, the inner product of the function that we transform times the basis, the corresponding basis vector. And similarly for the second, for bn. Okay, so this way I can find an and bn in this expression here. Okay. So this transformation, this Fourier transformation, is well defined now. The main conclusion from this part is that we can treat complex functions as vectors in a vector function space, and this space, of course, can be of infinite dimensionality, because as we discussed here, this coefficient n can be any number, in any integer number, right? It can be 1,000, billion, and so on. So theoretically, this series here is infinite, right? It contains infinite number of terms. This brings us to a very important concept in physics and engineering too, so-called eigenmode decomposition. Okay. So as an example, let us consider a string of a guitar, and this string is a physical system, right? And one can find the set of eigenmodes of this system. These eigenmodes, the first 4 eigenmodes of a string is demonstrated here, mode 1, 2, 3, and 4. So as you can see, they remind us this sinusoidal functions, right? But in reality, when we excite the string of a guitar, we get something like this, right? So this is one possible picture of the string, of vibrating string, and it doesn't remind us any of these eigenmodes. So what it is in reality, this real vibration of the string is a combination of eigenmodes, of the string eigenmodes. These eigenmodes are all orthogonal, and we can use them as the orthogonal functions in the representation, in the transformation like this, shown here. Okay, so it's not Fourier transformation anymore. This is a new type of transformation called eigenmode transformation, or eigenmode decomposition, right? So again, we have a physical system. We solve the system for its eigenmodes, and then we say that any evaluation of the system, like this vibration of the guitar string, can be represented as a combination of the eigenmodes, of the system eigenmodes. And this is one good example of a very general concept, very general approach that actually works for any system. So here I put as an example just 2 of them. The picture on the left shows us some acoustic response of a guitar demonstrated here. So this is a guitar, and then the authors of this paper, they measured basically the sound in different places of the guitar, and recorded the response. And then what they did the Fourier transform of the signal to the frequency domain. So this is the frequency domain. And here we see these peaks, right? So we call them resonances. And each resonance corresponds to the eigenmode of this system. Okay, so if I can define all the eigenmodes of my system, of this guitar, I can reconstruct the any response of the system of this guitar. At the same time, this picture on the right shows us the light scattering from some small nanoparticle. Okay, so this is I guess this is the theoretical spectrum, but in experiment it also looks the same thing. So what you do, you shine light beam on a small nanoparticle, and in response you get the spectrum like this. And we also see these resonances here, here, and here. So these all resonances also correspond to the eigenmodes of the system. Okay, so all these examples, just like the eigenmodes of the guitar, they illustrate this concept of eigenmode decomposition. Okay. So this is basically why we need this function space concept. Function space concept, and why we need to be able to work with functions as with vectors. Okay. And this brings us to the concept of Hilbert space that we already discussed. And put in simple way, in the context of, we can say in the physical context, right? So in the context of this course, a Hilbert space is defined as a complex linear space consisting of vectors or functions. So since this moment, we treat functions and vectors similarly, the same way. Endowed with a certain basis denoted as, like this. So the letter, this denotion can be different, right? So the main point here is that we introduce the basis that we use to describe this Hilbert space. So this space is characterized by its potential for infinite dimensionality. So the space can be of infinite dimension. And of course, the chosen basis is not unique because, again, as we already discussed, if we introduce a basis in some linear space, we can rotate the basis by any arbitrary angle. And that new rotated basis can be also used to represent any vector in this linear space. And since we introduce the basis, and only after that, we can represent any vector function in this space through this combination of the basis vectors and the projections of the vector on the corresponding basis vector. In quantum computing, we usually truncate the Hilbert space to the number dimension of 2. Okay, and use this concept as a building block. So, and this building block is called qubit or quantum bit. Okay, so we consider a quantum system that can exist in two quantum states, two quantum eigenstates. Okay, and the system, of course, as like this guitar string that can, for example, exist in these four different eigenmodes, but in reality it presented in a superposition of these four eigenmodes. Okay, so now our qubit, which is characterized by two eigen states and eigenmodes, can exist in the any superposition of these two eigenmodes. I want you to like understand this concept very clearly. So a qubit is a system with two eigenstates, and the actual state of the qubit is the superposition of these two eigenstates. Okay, linear superposition. We will discuss that in more detail in what follows, but here I summarize the mathematical objects we will need to talk about qubits and two-dimensional Hilbert spaces. Okay, so first of all, we introduce ket vector like this, right? So this, again, bracket notation. I refer to our last lecture probably, where we introduced all this. So ket vector, right, is the vector column, and the bra vector is the dual vector, which I get by this complex, this Hermitian conjugation operation denoted by dagger. Okay, so dagger is double combination. It's a transposition and complex conjugation, right? So we combine these two operations in one single element or one single operator called dagger. Bra vector is a dual vector to ket vector, and we get bra vector by dagger the ket vector. Okay. So if we have two vectors, bra and ket, we can construct this combination bracket, right? So and this is the inner product of the two vectors, B and A. And but if we exchange these two vectors, put vector A on first place, B on the second one, again, according to the basic matrix product operation, since ket vector is a column, bra vector is a string, as a result, we get this matrix 2 by 2, right? Because we multiply the vectors of the matrices row by column, right? And this vector, this row gets only one element, column of vector B gets only one element. That's why we fill up this matrix here by all the possible combinations of the components of vector A and B. And this matrix can work as a as a operator. Okay, so this is basically the result of this product. This outer product is the operator. So next, qubit, right? And the qubit gets two possible states and two possible eigenstates. Okay, and the easiest way to describe a state of a qubit is to introduce these two vectors here. Vector 0 with components 1 and 0, and vector 1 with components 0 and 1. So when I look at these vectors, I always imagine some sort of an atom with the ground state and excited state. You of course know that, like a system like a hydrogen atom, for example, right? You can excite the hydrogen atom from ground state to the excited state. And so when I look at these vectors, anytime I imagine something like this, so the 0 state corresponds to the ground level, ground state of my atom, and this state 1 corresponds to the excited state. Okay, and one way to look at this 1 and 0 here, like 1 here is the electron in the ground state, and then if we excite the atom transits to the state 1, and now the electron is in the excited state. So this is just a way how I look at these matrices, but for now it's very general way how we, and the easiest way how we can describe the state of any qubit. Okay, so vector 0 and vector 1. So very simple. So to represent a qubit in what follows here, we will use this qubit class from SymPy. Okay, so last time I encouraged you to go to this SymPy Physics Quantum and look through. They have a particular class for, or a library for quantum computation, which I like because we can reproduce these vectors in this way, in the way of zeros and one, Brian-Cat notation, which is very illustrative at this point. Okay, so maybe in what follows we won't be use this way of representation vectors that much, because we're going to focus more on Qiskit. But for at this moment, let us use this class qubit from SymPy Physics Quantum. Okay. In order to be able to do so, I import this class qubit from SymPy Physics Quantum Qubit here. And as I do so, I can work with qubit states, qubit 0 and qubit 1, just announcing them. So here, for example, I write this qubit 0, and this is exactly the state 0 here, this 0, 1 vector. And qubit 1, similarly, this is state 0, 1. Okay, and I just give a name 0 state, ZS, and 1 state, OS, here. So the result, the result is 0 state and 1 state. But now this is not just the letter, right, or graphic element. This is actually the matrix. Again, in order to be able to create bra vector, right, I need dagger operator. I need to create dagger operator, and to do so, I import also this dagger operation from the same library. And if I dagger the state 0, right, I get this 0 bra vector like this. And having these operations, I mean, this dagger and this qubit states 0 and 1, I can, of course, produce like more complicated things. I can, for example, compute this operation of the bra and cat written like this, right? Again, so bra vector first, the cat vector second, and here is the result. The state 0, 1. And this is just product of two matrices, right? 0 and 1 written here. So the bra vector is bra vector 0. It is this one, but transformed to the vector raw. Okay, and the state 1 is just this column here. So I can calculate this product of two vectors, and how I enforce my, I mean, this code to do so. I just write this do it, right? So I put this state, this product here in the parentheses, and then write do it, and this method enforces Python to compute this inner product here, and the result is, of course, 0 and 1. Okay, so when I take the product of two different vectors, 0 state and 1 state, I get 0. However, if I take the product of the same vectors, 0 and 0, I get 1. And likewise, if I do for the second one, for the state 1 and state 1, I also get 1. So I conclude that these vectors 0 and 1 are orthogonal. Okay, again, we introduce these vectors 0 and 1 to describe the state of a generic qubit. And why? One can ask why we can use these vectors to represent the state of a qubit. The answer is here. The answer is that these vectors are orthonormal, meaning that the product of any two, I mean, the product of two different vectors returns 0, and the product of the same vectors return 1. So the vectors are orthonormal. Yeah, the same way I can compute this. Sorry, I can compute this outer product. For example, here, if I remove this do it for a moment, right? I have the expression like this. So cat vector times bra vector. But again, these two vectors just two matrices, and I can actually compute the result of this too, right? And if I want to enforce Python to return this the result, I write dot do it, and it's supposed to return the result, which is not because I need to use qapply here. Yeah, this is tricky point. So let me return to this point a little bit later. So anyways, we can using this qubit operators and dagger, we can form the elements like this. So this is the outer product of two vectors. Sometimes we need to change from vector representation to matrix representation. And in order to be able to do so, I also import this representation function from SymPy Physics Quantum. And this allows me to, again, to represent this vector. Let me remove, for example, this one for a moment. And let's say I have this vector 0s, right? Which is 0 cat. Using this function here, I can return its matrix or vector representation 0, 1. And the same for this vector one state here. So using this operation, let me check what I'm doing here. So if I compute the yeah. So let us look at this outer product again. Okay, so this is the outer product that I wanted to basically compute here. The outer product, and the result of the outer product is the operator, the matrix 2 by 2. Okay. And what's the result of this? So I can find this result by using this representation to represent this result as a matrix. Okay. And the product of 0 state times 0 state is a matrix 1, 0, 0, 0. So this is the operator. This is the matrix that corresponds to the operator. And similarly, if I consider another one, like state 1, 0, 1 state times 0 state, 1 state times 0 state, the result is here, right? So this is the operator representation. This is the matrix representation of the same thing. And for completeness, I put all the 4 combinations here. Okay, so this is the result. So if I take the product of 0 state times 0 state, I get this matrix. 0 state times 1 state, I get this one, and so on. The state 1, 0, and 1, 1. So all 4 matrices. Why it's important? It's important because if I have any 2 by 2 matrix, like matrix ABCD, like this, I can represent this matrix using these 4 matrices here. Okay, so I can represent this ABCD matrix as A 0, 0 plus B 0, 1 plus C1, 0 plus D1, 1. This is the representation of this matrix here. If you compute, if you plug in the matrices for the corresponding operators here, you will get exactly the same matrix here. This is one important consequence. Another one is that if you consider the combination of the product of the same basis vectors, okay, so we have two basis vectors. One is 0, another one is 1. So if I consider the combination of 0, 0, which is the combination corresponds to the first basis vector, and second vector, right? So this combination corresponds to the second basis vector. And if I consider this operation like this, I will get the identity matrix 1, 0, 0, 1. It's easily seen from these two. If I take this one, this matrix, and add this one, right, I will get matrix 1, 0, 0, 1, identity matrix. And this holds true for any space and for any combination of basis vectors. So let's say I consider the space of dimension 10, then I will have 10 eigen states. I use the eigenstates as the basis vectors to represent any space in that, to represent any vector in that space. And if I compute something like this, right, the all combination of the 10 basis vectors, I will get identity matrix. This is rather important, and that's why I put this formula in a box here. Okay, so this is the rather general result. So next, as like, I will return to this example several times. So as like the real vibration of a guitar string is a combination, the superposition of eigenmodes of the string, like this. The same way, the state of a qubit is a superposition of these two states, of these two eigenstates, eigenstate 0, eigenstate 1. The simplest superposition that we can write at this moment is just this one, right? The sum of the two, the sum of the 0 state and state 1. Okay, so this is the equal superposition of two states, or we say superposition of two quantum states. However, we will require the all quantum states to be normalized to 1. Okay, just like any or all the eigenmodes or eigenvectors are normalized to 1. Similarly, we require that all eigenstates, or sorry, all states, all superpositions also normalize to 1. And let us check that this superposition here is normalized to 1. So how we do so? We do that in a way how we so basically we calculate the magnitude of this complex number like this, right? And then we need to divide each vector by the square root of this magnitude. So so here I write this superposition state qubit 0, qubit 1, and I multiply this state by the dagger of the same state, right? Which is bra and cat. So this is cat that corresponds to the superposition of two vectors, and this is bra that corresponds again to the superposition of these two vectors. And here is the result. So Python, SymPy, didn't compute the result of this. So in order to be able to compute the things like the expressions like this with multiple terms and simplify the things, I need this operation q apply. Okay, so I import q apply from SymPy physics quantum q apply. And now I apply this qapply function to this expression here. Okay, and here is the result. So one can compute this like very, it's very simple to compute. So it's basically just the product of two expressions, this and that, and the result is 4 terms. The inner product of 0 and 0, which gives us 1 because the state is normalized. Right, the second one is 0 and 1, which gives us 0 because the states are orthogonal. Then 1, 0 again is equal to 0, and 1 times 1 is equal to 1. So the result is 2. And this operation qapply returns 2, indeed, as we expected. So in order to normalize this state, this superposition state 0 and 1, I need to divide this state by square root of 2, right? Why? Because if I again multiply the state by the same state, it will return me 1. So this is the correct formula, this correct expression for the superposition of states 0 and 1. We need to divide this expression by the square root of 2. This state also is of particular importance because this is a state of perfect superposition of two basis vectors, 0 and 1. And since this state is important, if we give a specific name to this state, and we denoted this state by this state plus. Okay, so this state plus is the perfect superposition of two states, 0 and 1. So now when one can ask why we put 0 or why we use plus here, not minus. So indeed, this plus corresponds to so-called constructive interference, right? When one state like contributes constructively to the another one. So this is, I quoted this because it's not like what exactly happens here, but we can say for now that this is just like it works as a constructive interference. Like when we consider two waves two waves, they constructively interfere and amplify each other. However, we have another option here, right? If we put minus here. So this minus corresponds to the destructive interference, when like two waves destructively interfere and cancel each other or suppress each other. This is another state, and that's why we assign a special, like another name for this state, state minus. Okay. And so now we have two new states, state plus and state minus. Now I wonder if these states are orthonormal. To do so, I give the names to the states, right? Plus state and minus state here. So now I have these two new states. I can check that indeed these are my states. Plus state is plus, minus state is minus. And let us compute the inner product of the plus state times plus state. Let us compute just this one for a moment. All right. So indeed, the result is 1. So this state plus is normalized, which is good. But we expected that because this is the way we normalized. This is the way, or this is the reason why we introduced this factor 1 over square root of 2 to normalize this state plus. But let's check for the state minus. So the minus state also returns us 1. So this state is also normalized. And finally, let us check that the two vectors are orthogonal. So the result of their inner product indeed returns us 0. So the states are orthogonal and normal. That means that the states are orthonormal. And this just a new, since these two vectors are orthonormal, we can also use them as a basis to describe any state of a qubit. Okay, so now we have two different bases. The one is states 0 and 1. This is first basis, the simplest one. But we can also describe the same system, the same qubit, using this states plus and minus. And this is just alternative description of the same vector and of the same qubit of the same system. The result will be completely the same, regardless of which basis I use. But sometimes one is more preferable than another one. Okay. And of course, if I work in the basis plus minus, I can change the basis and go to the basis 0 and 1. These are the formulas how I do so, right? I can represent the basis 0 through the constructive superposition of state plus and minus, and state 1 as a destructive superposition of state plus and minus. Yes, and let's check that, right? Let's check these two formulas. So here I do what? Yeah, I basically I basically write this formula for this one and the both formulas here. 1 over square root of 2 and then times plus state plus minus state, and the same one for the minus state, right? And I compute this, and indeed I get 0 state and state 1. So these two formulas work, and we can use these formulas to transit between the bases from 0, 1 to plus minus. Yet there is another basis, the third basis, that also can be used to represent the state of any generic qubit. Okay. For now, we can name them plus I and minus I states. The difference between plus and minus, just appearance of this imaginary unit here before state 1, right? So we introduce the imaginary unit here. Again, these two vectors are also orthonormal. Let us check it here, right? So I introduce plus I state, minus I state through these combinations with imaginary unit. I remind you that imaginary unit in Python is 1j, not I. Okay, so yj 1j here. And then I compute the inner product of plus I minus I minus I, and then the inner product of two different vectors. Again, the vectors are orthonormal, and we can use these plus I and minus I states as a third basis to describe the same thing, the same system, the same qubit. So all these three bases are equivalent, and one can use each of them to represent the state of a qubit. Very good. So, do you have any questions thus far about this part?
Professor, I have a question. Yep. In this area, you have wrote complex without any complex function. So, is it? Actually, I don't understand this. This J, yes, here, this J, without writing any complex function in Python, but how did you do that?
So when I use 1J, I mean, when I import the library, I guess when I import math here, I can use this 1J as, I mean, the Python understands that 1J corresponds to imaginary unit here. So I don't need to specifically say that this is imaginary unit or this is complex valued function. It's all automatically done by uploading the corresponding libraries.
Okay.
Yeah, so Python is very, how to say this, high level programming language, right? It understands, so it's not just programming language, it actually understands the things like this. So when I put 1J, Python understands that this is complex unit rather than something else. So in this sense, Python looks like, or yeah, it looks like, for example, Mathematica. When we use imaginary unit in Mathematica, we also don't need to announce this this imaginary unit, right? It's already inbuilt. So yeah, this is the way we use it here. So no need to announce this imaginary unit. Just again, just bear in mind that traditionally we denote imaginary unit as I, but in Python it's 1J.
Thank you.
Yeah, thank you. Thanks for the question. Do you have any others? All right. So if no, let me like quickly summarize what we've discussed so far. The key things, right? The first thing I want you to like very well understand is that we can work with functions as with vectors by introducing this function vector spaces and the inner product between two functions defined in this boxed formula here. Okay. Since we introduce this operation, this inner product of two functions, we can represent any function using these functions as a basis. One typical example of a basis is sine cosine functions, and the corresponding transformation of a function by this set of cosine and sine functions is known as Fourier transform. This very well known, famous Fourier transform that we use every day, actually. So this is very important concept. Any physical system, I mean, it's hard to find example of opposite, right? So like any physical system in reality, regardless of the nature, like atom, guitar, resonator, radio, antennas, literally anything, can be described by eigenmodes. Okay, so like let's say another example, antenna. If you drive a current in the antenna gets some current distribution over the antenna. And this current distribution can be represented as a linear combination of eigenmodes of the antenna. The eigenmodes will be like very different. So this is just example of the guitar string. That's why these ends of the guitar string are fixed, right? In other example, it would be functions, some other functions. The very important point here is that eigenmodes are orthonormal. They are orthogonal. And since they are orthogonal, we can represent any function using these eigenmodes. Okay. And speaking about quantum, we start from the basic building block of any quantum system, which is a qubit. a qubit is a system with two eigenmodes. So for example, here I draw 4 eigenmodes of the string. The qubit is a system with two eigenmodes. And these eigenmodes are orthogonal. And the qubit itself can exist in any combination of these two eigenmodes. Okay? The simplest eigenmodes or eigenvectors or basis vectors, if you wish, these words are like, they denote the same thing. These eigenmodes, eigenvectors, eigenstates, they represent the same thing. And these two vectors are the simplest the simplest eigenvectors. Eigenvector 0 and eigenvector 1 with components 1, 0, 0, 1. Of course, this choice of basis is not unique. And we can, for example, introduce the constructive and destructive interference or combinations or superpositions of these two states, 0 and 1. This state plus and this state minus. And this is another basis to describe the same thing, to describe the same qubit, okay? The same state of a qubit. Yeah, so we concluded with introducing the yet another one, the third eigen, the third basis with state plus I and minus I. This is the most important things, I believe, by this point. And this concept of eigenmodes and eigenvectors is very generic. Again, if you describe antennas, you use the concept of eigenmodes. If you describe the light scattering by nanoparticles, like in my lab, we use eigenmodes. If you describe the sound from a guitar, you use eigenmodes. Literally anything. This is the eigenmodes, of course, depend on the system, and these are different functions, and etc. The main point is that the eigenmodes are orthogonal. If you compute the inner product, you get 0. They are orthogonal. All right, so having said all this, I transit to the new part, the new chapter of the course, and that we will continue next time. Basics of quantum mechanics. I believe the best way to formulate the basics of quantum mechanics is the way of postulates. So I believe I was able to summarize all the concepts, or like the main concepts of the concepts we will rely on in the form of just 2 postulates. So some of them are rather simple, some of them like require a little bit of thinking, but 10 postulates. So let us start with the first one. So the first postulate, again, you would never find these postulates in textbooks. It's something like that. This is like my way to represent the quantum mechanics, right? In other books, you would find other alternative ways. I prefer to do this part, or to teach this part in this way, in terms of postulates. Okay. again, if you would try to Google like postulates or 10 postulates of quantum mechanics, or so, you wouldn't find anything, because this is my way to represent the things. All right, so let's start with the postulate number one. The postulate number one, as I formulate this, says that the state of a quantum system is represented by a vector in the complex Hilbert space. Okay. So let's say we have some quantum system. It can be like small particle, electron. It can be some sort of an atom, hydrogen atom, helium atom, etc. It can be like a molecule. It can be even a quantum computer. So let's say I have a quantum computer. Still, the state of all these systems, regardless of like what it is exactly, electron or quantum computer, the state of the system is represented by the state vector. State vector, we call it psi vector, in a complex Hilbert space. Okay, so for example, if I describe a qubit, which is a system of two eigenstates, this psi vector will be represented by these two combinations, C00, C11, right? However, of course, a real system contains a lot of, or it is described by much larger Hilbert spaces of larger dimensions. But still, the state is represented by a vector. This vector exists even without introducing the basis. Okay, so vector is a geometrical thing. Vector exists regardless of the coordinate system. Like, let's say you drive a car, your car gets a specific velocity. Velocity is a vector, right? Because it gets the magnitude and direction. And the velocity of your car is a geometrical or physical thing. It exists regardless of the coordinate system. You can describe the moving of your car by choosing this or that coordinate system, and that will affect the components of the velocity of your car, but the total length of the vector and the direction of the vector won't change. So the vector exists regardless of the basis. And just like with your car, the state of a quantum computer is also a vector in a complex Hilbert space. And in order to describe this vector, we introduce the basis. For example, if I introduce this basis like drawn here, all these vectors, these blue lines, states 0, 1, 2, 3, n, they all are orthogonal. They all orthogonal. And having introduced this basis, I can represent this vector state of my computer in this way, through this combination of the basis vectors and the projections of the vector on each corresponding basis vector. I hope that's clear. Here I put just a couple of examples. The first example is a particle passing through a slit in a in a screen. Okay, so for example, I have a like an electron or a photon, and this photon is represented in state psi 0, okay, and moves like this towards the slit in a opaque screen. Okay, so what experiment tells us is that after this slit, the electron or the particle can move any of these directions, any of these directions. Like if I put my detector, I can find the electron in this state here, or this state here, or this state here, but I don't know which way the electron will go after the slit. And before measuring the particle, the electron, in which state the electron is, I have to take into account all these possibilities. So my electron after the slit can go either way. And in fact, it's an infinite number of directions. After the slit, I have infinite number of directions in which the electron can go, right? So for the electron, after the slit, this series contains infinite number of terms, because the number of directions the electron can go is infinite. Another example is is electron like this. So let's say my electron passed through one slit, and I've got many states for the single electron in which the electron can exist after the slit. However, I can put another screen with two slits in it, like shown here, and this way I will select just two states from this infinite set, right? So I truncate this infinite number of states to just two possible states, right? And this is an example of a qubit, when the particle can go through this path here or this path here, but no more. So this is just two options here. And again, before we measure which path the electron has chosen for its move, we have to take into account the both of them, but probably with different probability, which we will discuss, taken into account by this coefficients C0 and C1. There is a countless number of examples of systems with just two possible states. Okay, for example, the spin of electron. We will discuss in more detail, but you're probably aware that a spin is a system that can get only two directions in a magnetic field. So you have electron, you apply a magnetic field, the spin of the electron can point along the magnetic field or in the opposite direction. So just two options, along and opposite. And we can consider these two as the eigen states of the electrons. Points up, points down, these are two eigenstates. And the electron, before we measure it, must be considered to be presented in these two eigenstates in the same time, like simultaneously. However, in experiment, it can be found only in the state up or the state down, and not in any other possible, states or any compositions. So only just two options here. But before we measure it, it must be thought as being in the both states in the same time. Another example of the system with two states is the polarization of light, right? You probably know that the light is a vectoral field, and if we consider a plane wave, the electric field of the plane wave can oscillate or up and down or left right. Okay, so again, these two options here, these two possible states, state like vertical state of polarization and horizontal state of the polarization. And of course, there are other systems, just like I already mentioned, like I say I have an atom gets the ground state and excited state. I say that the state 0 is my ground state, state 1 is the excited state. And before I measure the atom, it must be thought as being present in the combination of the two, in the state 1 and 0. Okay, it's like combination of the two states. However, when I measure the atom, I can find it either in state 0 or state 1, but no other options I have. So just two options for the experiment. So this is the postulate number 1. The quantum state is represented by a vector in a complex Hilbert space. Second postulate, which is also known as the Born rule. So the Born rule tells us more about this coefficients Cn. So the coefficients Cn are probability amplitudes of finding a quantum system in a particular eigenstate n. Okay, so let us return, for example, to this formula here for a qubit. So this is the general state of a qubit. C sub 0, state 0, plus C sub 1, state 1. The vectors 0 and 1, as we discussed, these are eigenvectors or eigenstates in which the system can be found in experiment. However, the probability of finding the system, for example, in the state 0, is given by this coefficient C sub 0. And likewise, for the state 1, it's given by this coefficient C sub 1. So for example, if I consider an electron like this, this state 0 points down, spin points down, state 1 spin points up. If I measure the electron, I can find it in the state up or state down. And this C sub 0, C sub 1, they describe the probability of finding the corresponding state. However, these coefficients, they are complex valued. So they are complex. They describe not just probability, but probability amplitudes. Okay? So the actual probability is given by the absolute value squared of this coefficient Cn. So what I do here, yeah, so here I show how to, for example, introduce this coefficient C sub 0, C sub 1 by using SymPy symbols. And here I specifically indicate that these coefficients are complex valued, right? And then having these coefficients introduced, I can write the general state of a qubit using like this, right? So C0 is this coefficient 0, C1, and they both multiply by the corresponding state of the qubit. Right, so this is the result. So this is the general state of a qubit. And then what I do next, yeah, I multiply this general state of the qubit by this zero eigenstate of the qubit, right? So this, what it means to find the inner product of two vectors. It basically means the operation of finding the projection of one vector onto another one. So this is the this is what I'm doing here. This is the projection of the state of the qubit on the corresponding eigenstate, on the zero eigenstate. And as expected, it returns me C0. So C0 is the projection. Let me get to this picture here. Okay, so C0 is the projection of this quantum state psi vector on the zero eigenstate. So this distance here is described by C0. Likewise, C1 is the projection of the psi vector on the eigenstate 1, and etc. for all other eigenvectors. And we are working in the Hilbert space. So this is not just distance, this is complex distance or complex projection, right? So because these C coefficients, they are complex valued. And then finally, in order to find the probability of finding my state in the state 0, I need to take the absolute value squared of this coefficient. So in experiment, what you do, you have, for example, this spin in a magnetic field, and then you measure this spin, for example, 1,000 times, and then find the experimental amplitude. And this way you will get the, or you measure these probabilities of state 0 or state 1. And of course, if we have, and of course, this probability amplitudes are supposed to be normalized to 1. So if I sum up all the probabilities, right, I'll get 1, because 1 is for like 100% probability. All right. So yeah, and I guess the last one, the last postulate for today, we're running out of time, is the postulate number 3. So postulate number 3 says that physical observables in an actual system are represented by Hermitian operators. So you remember last week we discussed like a lot about this Hermitian operators, and we say that Hermitian operators are operators that remain unchanged upon this dagger operation, this transpose and complex conjugation, right? So if this operator doesn't change upon the dagger operation or Hermitian conjugation, the operator said to be Hermitian. And this postulate 3 basically says that the things that we measure in the lab, when we measure some quantum object, some quantum system, like quantum computer, the things that we measure must be described by Hermitian operators. Why? Again, I refer you to the previous lecture, because Hermitian operators have real valued eigenvalues. So the operator itself complex valued, but this complex valued operator or complex valued matrix has real valued amplitudes. That's why we use Hermitian operators to represent physical things, because what we measure is always real valued, not complex, always real valued. And another property of Hermitian operators is that eigenstates of Hermitian operators are orthogonal. Okay, so we can use the eigenstates of Hermitian operators as a basis in the Hilbert space to represent a state of a quantum system. Okay. Yeah, so this is basically said here. So for example, if in classical physics we have the quantities like position, radius vector, momentum, the energy, right? In quantum mechanics, we say that we promote these quantities to Hermitian operators. And the way we denote that these quantities are operators, we put a hat on top of these letters, right? So this is the operator of position, this is operator of momentum, and this H, sorry, this H operator is the operator of energy, and it gets a specific name. The name is Hamiltonian. And this Hamiltonian is a very, very important thing in the quantum theory. This Hamiltonian. So basically, when you need to describe something like some sort of atom or molecule, any quantum system, you first describe the Hamiltonian. You introduce or write or guess the Hamiltonian, and then all the things you get from the quantum system basically are contained in the Hamiltonian. So the Hamiltonian is a very important thing, and we will get back to this in what follows. But today, yeah, so this statement basically tells us that the eigenvalues of the Hermitian operator is real values. That's why we can use them to describe the physical quantities. And also the eigenvectors are orthogonal, so we can use them to represent the state of the quantum system as a basis. And finally, there is an example. Example of energy operator, Hermitian Hamiltonian of a general qubit in the energy representation. So a few words about representation. So let's say I have an atom. I can describe, so I can measure, for example, the coordinates of some elements of the atom, right? So electrons, nuclei. I can measure position of the atom. I can measure momentum of the atom. I can measure energy of the atom. And all these quantities in quantum represented by Hermitian operators. And the Hermitian operators, as we said, they have orthogonal eigenstates, which can be used as a basis in the Hilbert space. So let's say I measure, or I'm interested in position. Then I use the eigenvectors of the position operator and got some result. However, like another day or like another researcher might be interested in momentum of the atom, and they will measure the momentum, and they will work in the momentum eigenvectors for the same system. And another day we might be interested in energy, and we could work in the energy and energy representation and use energy eigenstates to describe the same system. The same system. This is very important. So we can use different bases to look at the same system. And we call that we are in a particular representation when we use a particular choice of the eigenvectors. Okay, so this is why I put this example here. So let us say that let me actually put, since I always use this lines here for the example. Right? So the Hamiltonian of a two-level qubit system. So as we said, the qubit is a system with two states, and it can be energy states. So here I put, for example, this picture, like the demonstrating a complex structure, like complex spectrum of a molecule, and we can always work within this area of interest, so we don't excite other states in the system. Right, so as we work within this energy gap, energy spectrum, we only interested in these two states, or we can only affect only these two energy states. And in this case, in this approximation, the system is a good representation of a qubit, a system with two energy levels. And now I can say, for example, I want to describe this system in a position basis. Then, since the system is so complex, contains a lot of electrons, positrons, neutrons, and I have to take into account the position of all these particles in the system, the description will be very, very complex. So it's very hard to describe such a system in a coordinate representation or in the momentum representation too. However, if I'm interested in energy, and if I'm working in the energy representation, so I measure energy in the system, right? Then I immediately say that, oh, the energy of this eigenstate is a EA, which is eigenvalue, right? That is associated with this lower eigenstate. And the corresponding, and the energy of the upper state is EB, the energy of the excited state. And then I say that, yeah, so the Hamiltonian, which is the operator of energy, must contain this energy of the ground state and energy of the excited state as the eigenvalues of the corresponding matrix, right? So this is the only way how, I mean, this is the Hamiltonian of the system. It's just a matrix with two numbers here, there, on the main diagonal. Again, in this particular case, if one would work in the coordinate representation, it would be very hard to describe the system, to write down the Hamiltonian in the coordinate representation. However, if I am interested in energy and I'm interested in the energy representation, the Hamiltonian is easily written. It's just a matrix 2 by 2 for the system, which looks like that. So this is basically all I needed to share with you today. Let me stop the recording and then we can discuss.